coming back to the notion of the intersection form. In the last lecture, I mentioned the intersection form, which is one of the fundamental objects in four-dimensional topology. And the setting that I discussed last time is if we have a smooth, compact, connected four-manifold, which you can always assume to be connected. Also, it did say connected. Then there's a version of the intersection form over R using the LeBrun cohomology, which I discussed last time. If you have a pair of closed two forms, you can wedge them together and integrate on the manifold. And the answer only depends upon their LeBrun classes. If you change either form by adding D or one form, it doesn't change this integral by Stokes theorem. So this is actually a cohomological operation. And if you're working over R, I mean these cohomology spaces are finite dimensional spaces. This is a symmetric, non-degenerate form. The fact that it's non-degenerate is a manifestation of Poincare duality. And over R, a non-degenerate quadratic form can always be diagonalized. It's similar to a form corresponding to a matrix with a certain number of plus ones and a certain number of minus ones on the diagonal, where the number of plus ones is the maximum dimension of a subspace on which the restriction of this form is positive definite, and B minus would be the maximal dimension of a subspace on which the restriction of the form is negative definite. And so I brought this up last time because it is used to define this important invariant of a four-manifold, the signature, which is the difference between B plus and B minus. Now, if you think about it a little bit, this is actually the index of a certain elliptic operator. The index theorem predicts that such things are actually representable in terms of characteristic classes. And in this case, the relevant theorem was actually first pointed out by René Thom at least a decade before the index theorem, or probably 15 years before the index theorem. So he pointed out on a four-manifold that this invariant, the signature, is actually the same as the first Pontryagin class of the manifold integrated against the fundamental cycle. So in particular, that means that you can represent the signature by a curvature integral. You take any connection on the tangent bundle, then you can write down a polynomial in its curvature whose integral will actually give you the signature. And that was the source of a surprising formula we saw last time, that this signature is actually something that can be computed by a curvature integral. Now, of course, you can also describe what's been going on here. This is really something that we could describe in terms of the singular cohomology over R. So LeBrun cohomology is isomorphic to the singular cohomology, but the advantage of the singular cohomology is actually only depends on the homotopy type of the manifold, unlike when you describe things in terms of differential forms. So this is not just an invariant of the smooth manifold. It actually only depends on the homotopy type of the four manifold. And so the signature is actually a homotopy invariant, and that's related to various theorems about the invariance of the, so for example, if you wanted to see the topological invariant, there's a beautiful theorem that says that rational Pontryagin numbers are actually topological invariants, even though they are usually first written down in terms of the tangent bundle, which you can't talk about the tangent bundle if you don't have a smooth structure. Now, there is a deeper story going on, though, if we instead use integer coefficients for our cohomology rather than real coefficients. And so there's an interesting piece of number theory arithmetic that's behind part of the story. There is a version. If you think of the real cohomology is simply you take the integer cohomology and you tensor with R, then, well, you could say, well, there is some form on here, but in fact, it actually takes, given two integer classes, it actually, the product via this intersection form, so-called intersection form, is actually actually an integer. And that's despite the fact that you could say, well, here this vanishes on torsion. If you have a torsion element here, because this is a homomorphism in each category, has to kill, and the image is in Z, then this actually kills torsion. And so you can think about the second integer cohomology modulo torsion as just a lattice in the real cohomology, namely that it consists of de Rham classes such that the integral on any compact-oriented surface in the manifold is an integer. But the surprise, if you thought about it that way, it wouldn't be obvious that this map would actually take integer values. In fact, Poincare duality tells you a little bit more. If you write down a matrix that represents this modulo torsion, and we'll come to that in a moment, it turns out to be a unimodular form. Now, the geometric interpretation of this is first to remember that H2 of a manifold with Z coefficients, and actually this would work for rather general topological spaces. So here I'm going to be using a manifold and use smooth complex line bundles. So that depends on the smooth structure. If you take smooth complex, so the fiber is C, and these are smooth vector bundles over C of rank 1, then in fact the complex line bundles on the space modulo isomorphism are exactly isomorphic to the second cohomology with Z coefficients. Now, if you know the way you classify bundles in terms of classifying spaces, you can see this in a different way. But there's a direct way that's extremely nice and elegant in this context, which is, so what is the map? It's that any complex line bundle has a first Chaire class, which is in H upper 2 with Z coefficients. And if you just think about cohomology in terms of check cohomology with Z coefficients, or more generally sheaf cohomology, there is a short exact sequence. Integers go to smooth complex value functions to non-zero complex value functions with multiplication as the operation. So this is an exact sequence of sheaves of abelian groups. And when you look at it on when you take the long exact sequence, because the smooth functions are a fine sheaf, but they have their higher cohomology is non-trivial, so you get an isomorphism between these are isomorphism classes of complex line bundles, and these are and this is the second integer cohomology. Now, if you think about it in that way, there's also a very direct way of seeing Poincare duality. Poincare duality over dimension 4, H upper 2 will be isomorphic to H lower 2, because these are complementary dimensions. But that actually can be realized in the following beautiful concrete way. Take a smooth complex line bundle over your manifold, and then take a generic section. And generic means that it's chosen so that it meets the zero section transversely. When it does so, then the real dimension of the fiber is 2, so the zero set has codimension 2. That's a surface in the Four-Manifold. And so that actually gives you a way of going between an element of H upper 2 to an element of H lower 2, namely, given an element of H upper 2 represented by a complex line bundle, take a generic section, you get a surface that has a homology class. The pairing between two first Chaire classes here would be, well, represent one first Chaire class in terms of its Poincare dual as a surface in the Four-Manifold, and then what you can do is restrict the other line bundle to it and take its first term class integrated against the other surface. And so, but when you say, well, what is the degree of a line bundle on the surface? What you're actually saying is take the restriction of one line bundle to the others, to the surface that represents the Poincare dual of the other class, and say, for a generic section, how many zeros does it have? But on the other hand, you could also have represented the other class by just saying, take a generic section of that which is transverse to the first surface. And what you find out then is that the reason this is called the intersection form is that here what you do is represent two homology classes by smooth surfaces which are transverse to each other, and you count their intersection points with signs. If they're both oriented, the ambient manifold is oriented, therefore every intersection can either be consistent with or opposed to the ambient, the two, so the orientation on this surface could be, and on this surface they determine an orientation at the intersection point that could either be the orientation of the ambient four-manifold or it could be the opposite one. All right, so that's why it's called the intersection form. So a very special case of this is to take the self-intersection of a class. So self-intersection, that sounds like a crazy thing. I have a surface and I want to take its self-intersection. You're saying, well, it intersects itself in infinitely many points. But we're asking about the homology class. So you take a generic perturbation take a surface, take a generic perturbation of it, and see how many points these two surfaces meet in. And so you take two surfaces in the same homology class, you can take one surface and then take a generic perturbation of it and ask how many points do they intersect in counted with signs. But a different way of saying this is if we think of that cohomology class as being represented by the first term class of a line bundle, what we can do is integrate that on the surface itself. That's the meaning of the self-intersection. But if we've taken our surface sigma to be given by the vanishing of a generic section, its normal bundle is isomorphic in a canonical way, just by the derivative of the section. The normal bundle of this zero set will be isomorphic to the restriction of the line bundle. So a different way of saying this is that you're taking, you represent your surface by, you represent your cohomology class by, as being the Poincare dual of some surface. That surface has a normal bundle. This is a smooth embedded surface. And now what you can do is take the first term class of its normal bundle, thought of as a complex line bundle. Well, you don't want to say it. You want to think of it as a real bundle, just an oriented real bundle that has an Euler class. That's the same thing. So the first term class of a complex line bundle is also the same as the Euler class of the underlying rank 2 real bundle. And so here what you're really saying is you take the Euler number of the normal bundle of your representative surface. That's kind of interesting, because if you think about what's happening here is if you use the tubular neighborhood theorem, your surface has a neighborhood which is diffeomorphic to its normal bundle. What you're really doing is taking, in the normal bundle, take a generic section, that's another representative in the same homology class, see where they intersect. All right, so it's important to now observe that there is a relationship, after all, between Z and Z2 cohomology, because there's a short exact sequence of groups, and that actually induces a natural map from the Z cohomology to the Z mod 2 cohomology. And if you take the reduction mod 2 of the second Stiefel-Whitney class of the normal bundle, the reduction mod 2 of the Euler class of the normal bundle, that's the second Stiefel-Whitney class of that rank 2 bundle. And then there's a little calculation, which I shouldn't beat a dead horse too much. Right now we just said that mod 2, the self-intersection of a homology class or of a cohomology class, is the same as you take the second Stiefel-Whitney class of the normal bundle and then pair that with the surface. On the other hand, the total tangent bundle restricted to the surface is just the sum of the tangent bundle of the surface plus the normal bundle. And when you work through it, and I won't be that horse here, the point is the second Stiefel-Whitney class of this surface is actually 0. It's a mod 2 class. The Euler characteristic of a surface, of an oriented surface, is even. It's 2 minus twice the Euler characteristic, or the 2 minus twice the genus of the surface. That's 0 mod 2. So in fact, you find that actually the second Stiefel-Whitney class of the ambient four-manifold is restricts to the surface as the second Stiefel-Whitney class of its normal bundle. And now that gives an interpretation, a very, very important interpretation of what is the self-intersection of a surface mod 2. It's the same as the second Stiefel-Whitney class paired with the surface. Now this turns out to give, so I defined previously the notion of a four-manifold, an oriented four-manifold is spin if W2 equals 0. We haven't actually given that any geometric content yet, but here you start seeing that the intersection form tells you, so if you have a self-intersection that is odd, that means the second Stiefel-Whitney class of the four-manifold can't be 0. So a necessary condition for being spin is the self-intersection of any class has to be even. On the other hand, we could go back and just, the third cohomology is Poincare dual to the first homology. And in this sequence relating the integer cohomology to the Z mod 2 cohomology, if the manifold is simply connected, for example, or if more generally H1 with Z coefficients vanishes, then you'll find that actually the reduction from Z cohomology to Z2 cohomology in dimension 2 is surjective. Any element in H lower 2, and this is where the second Stiefel-Whitney class lives, that actually has to come from something in the integer cohomology. And so in the simply connected case, you can always determine whether W2 is non-zero or not. Actually, W2 always has integer lifts, and you can always determine whether W2 is 0 or not simply by looking at the pairing of that particular class with other cohomology classes. And so this is a beautiful corollary of a more general theorem by Wu in the early 1950s. If M is a compact simply connected manifold, it is spin if and only if its integer intersection form is even in the following sense. It's saying that every time you take an integer class and you pair it with itself, you will have to get an even integer, right? So so in fact the more general story is, this is called Wu's relation, that the self-intersection mod 2 is the same as pairing the second Stiefel-Whitney class with that class. This looks crazy because you'd say, well, this side is linear in sigma, in the class of sigma. This side, well, that's quadratic. But in Z mod 2, things that are quadratic are linear. It's algebraists take this for granted, but but for the rest of it, it's sort of a surprise. All right, so if whenever you take an integer 2 class, an element of the second cohomology with integer coefficients, and you take self-intersection, if that's always even, we say that this intersection form is an even form. And otherwise, you say that it's odd. Well, but concretely, that's easier to test. If you can find one class whose self-intersection is odd, it's an odd form. So odd means there is one class such that its self-intersection is an odd integer, whereas if you do this, if that never happens, so being even is actually kind of a harder thing to detect. You have to consider all possible self-intersections. So a warning is, so this works for simply connected manifolds. It works more generally if H upper 2 has no 2 torsion in it. But it will not work in general. So here's an example. Suppose you take S2 times S2, and there are free Z2 actions on S2 times S2, and those will turn out to have second Benny number 0. So there is no, the only element of H upper 2 with real coefficients would be 0 on such a space. Now actually there are a couple of different Z2 actions. If you take the one that's given by the antipodal map times the antipodal map, so here I'm taking S2 times S2, there is a Z2 action which what you do is simultaneously on both factors apply the antipodal map. Right? So on each factor that reverses the orientation, but you have the product of two things and it's orientation reverse on both factors, so that's orientation preserving. This quotient is the simplest example of a rational homology sphere. It's actually in dimension 4. This is something which, if you were looking just with Q coefficients, it has the same kind of cohomology as S4, even though it's topologically very different. It's not simply connected, in fact. It has fundamental group Z mod 2. So this particular one, you can check that this is not a spin manifold, even though the only class you could test it on would be 0. And by the way, if you think this is an innocuous example, if you take the connected sum of this example with anything else, it will not be spin. And the reason is that the diagonal class, okay, it doesn't show up in the homology with Z coefficients, but it shows up with Z2 coefficients. And really, the underlying Wu theorem is about homology and cohomology with Z2 coefficients. So if you to Wu's relation that you can understand W2 in terms of self-intersections of classes, that's true in general, but you have to use Z mod 2 cohomology. The thing that's special in, say, the simply connected case is that every Z2 class comes from a Z class for second cohomology. All right, so if we've been thinking about this so-called intersection pairing over you can say it's on the second homology, or by Poincare duality that's on the second homology, and in both cases you can just say, well, it's that mod torsion. So here, this is just this is now just the sum of a certain number of copies of Z, where that number is called the second Betty number. And you can represent this intersection formed by a B2 times B2 integer matrix, and Poincare duality says this has to actually set up an isomorphism between the cohomology and the dual of the homology, mod torsion. And so this is actually a matrix, it's an integer matrix that has determinant either plus or minus 1. So these are so-called unimodular symmetric forms. And of course, rather than talking about the intersection form, one could talk about the intersection matrix, but of course that's relative to a particular basis. So you really want to think of the intersection matrix up to similarity transformations. There's an action of SLB2 with Z coefficients on it, so by similarity. Okay, so actually, just by changing homology basis, any two similar matrices would arise from the same four-manifold. So let's just see some simple examples. So last time I showed you the key example of the connected sum of J copies of CP2 with K copies of CP2 bar. And remember that CP2 bar here means you take CP2 and you give it the reverse orientation, and the connected sum is this operation where you throw a standard ball out of a pair of oriented manifolds, and you glue the boundary spheres by, for example, a reflection. So you want it's set up so that you have an orientation on the entire manifold here, which is consistent with the given orientations on the two pieces. All right, so if we look at that example, there's an obvious basis here. What you could say is that, so in CP2, you have a CP1, right? And that generates the homology. So you take a complex projective line in the complex projective plane, and if you move that line a little bit, its generic perturbation meets it in one point. Now what you can do is now you leave that surface in the CP2 cut somewhere else, and now you go on maybe a CP2 or a CP2 bar, and you either have a complex projective line that gives you an S2 that's contained in the next thing. With respect to those bases, then in fact the intersection form you would see is the one I wrote down before, but here I was thinking there of over R, this is over Z now. So the intersection matrix for connected sum of J copies of CP2 and K CP2 bars has, J plus ones on the diagonal, K minus ones on the diagonal, and the fact that there are no. So notice that if you take an S2 in the first copy and an S2 in the second copy, they're not going to meet. You kind of carry out the surgery in such a way that they don't interfere with each other. So that's why this is a diagonal matrix. All right. So the shorthand for this would be to use +1 in angle brackets to denote the 1-by-1 matrix with entry +1, and you could do the same thing. -1 means a 1-by-1 matrix whose entry is -1, and now when you take a direct sum here, it means take these as blocks to build a bigger matrix. All right, so the shorthand would be to say that the intersection form of J CP2 connected sum K CP2 bars is J times +1 times plus K times -1. All right, so on the other hand, if you now check, is this an even or odd matrix? If you just take the intersection form of, let's say, the first basis vector in this basis, it'll have self-intersection 1. So this is an odd form. The second Stiefel-Whitney class of this manifold is non-zero. It is a non-spin Four-Manifold. Now, another interesting example would be, I mentioned S2 times S2 a moment ago, but let's not mon out by anything now. If you just say, well, on S2 times S2, you have an obvious basis given by the first factor and the second factor. The first factor you can slide it around so it doesn't intersect itself. The same for the other factor, but the two things meet each other in a point. And so what you find is the intersection matrix just has ones off the diagonal, 2 by 2 matrix with ones off the diagonal and zeros on the diagonal. And so here, to make it more concrete, this is analogous if you were to try to understand the intersection form on the first cohomology of a surface with Z2 coefficients. There's an intersection matrix there also, and you would take the two factors would be the generators. It's analogous, but don't push the analogy too far. Something that you can look at. All right, so if you now work out, so if you take the self-intersection of Mn with itself with respect to this matrix, little exercise, the answer is 2Mn. That's always even, and so this is an even form. And so we're in a situation where this is a simply connected Four-Manifold, and that tells us its second Stiefel-Whitney class is 0. This is a spin manifold. Similarly, a standard abbreviation, it's not a very nice one. People often use boldface H for this matrix and say that it's the hyperbolic matrix. Well, terrible idea, because H also stands for homology and cohomology. H stands for everything, right? So this is kind of the worst possible notation, but it's standard. So I'll follow this, and I simply use it's in black and a boldface font. So that matrix H shows up if we take a connected sum of S2 times S2 with itself a bunch of times. You simply again have an additive picture where you simply are taking a block matrix where you have it's made up of two by two blocks, more or less going down the diagonal. So this, by the same reason as before, is even. This is a spin manifold, which you can check in other ways, and so this connected sum of S2 times S2 is spin. Now the next interesting example is related to the Dinkin diagram, which in Lie group theory you would see associated with the Lie group E8, which is one of the really exotic, it's one of the exotic groups. It's not one of the classical compact groups. Here, there's a role for its Cartan matrix. And if you don't understand the things I just said about Lie group theory, forget it. So people in Lie group theory will talk about the Lie group E8. What we're actually interested in is there's a certain matrix. The Dinkin diagrams are actually recipes for writing down a certain matrix, and in Lie group theory, those are the Cartan matrices. So here, this is what's called a simply laced Dinkin diagram. No edge is a multiple edge. So we have 8 vertices, and each vertex is to be thought of as a generator of, let's say, R8 or Z8. And then there's a matrix where the self-intersection of each of these basis elements is -2. But -2 is on the diagonal. That's the first part of the algorithm. And the next thing is that if there is an edge between two dots, then the corresponding basis elements have intersection 1. So for example, the first and the second have intersection number 1. And that's true all along, except there's this one weird case which actually doesn't just intersect these 2 neighbors, there are 3 neighbors. And so the last, numbering it so that this one is the last, there is this surprising off-diagonal piece. So the surprise here is that if you check it, this is a unimodular matrix. It's actually an invertible. It's invertible over the integers, and it's called E8. And if you want, that's just saying that there's some standard 8x8 matrix which is called E8. Happens that E8 comes up all over the place in mathematics. There are physicists that are trying to find out what's the deeper meaning of this. A lot of mathematicians would just say, I don't know, it's got lots of nice properties. Maybe they don't have anything to do with each other. So this is an even, you notice, you start saying, well, self-intersections seem to be even numbers. It's not clear. Really, this is an even negative definite unimodular form, and its signature, which would be, if you were to now tensor with the real numbers, it would turn out that, well, it's because it's negative definite, and it's it lives in dimension 8. The signature is -8, so it corresponds to b plus is equal to 0, b minus is 8. So this is a piece of algebra now. There's a nice book by Chaire. There's also a nice book by Miller and Hilgermuller where you can see these things explained. If you have an indefinite, so this is not for positive definite or negative definite intersecting forms. Otherwise, if you take indefinite unimodular forms, they're actually classified by their rank, their parity, and their signature. So any odd indefinite unimodular form is actually isomorphic to this diagonal one we saw for the connected sum of CP2s and CP2 bars. Any indefinite one up to sign is a sum of a certain number of copies of E8s and a certain number of copies of the intersection form of S2 times S2, that hyperbolic matrix. All right, so the warning is that this does not work for definite forms, and so Jack Milner was really the first person to point out the importance of the intersection form and for studying four-manifolds, and he became obsessed for a short time before he moved on to other things in trying to see what this would say about classification of four-manifolds. So if you're looking for positive definite or negative definite forms, there are a lot more than these. the most famous ones are even, but there are also some odd ones. So on the other hand, what Milner had shown was that if you have two compact simply connected four-manifolds, they are orientedly homotopy equivalent if and only if they have the same, if and only if they have isomorphic intersection forms. Now, so his argument is beautifully concrete. You start off with the bouquet of spheres as the generators, and then you glue on a top cell according to the intersection form. And then he shows that actually, that up to homotopy equivalence, those spaces actually exhaust all possible four-manifolds. On the other hand, Rochlin in the Soviet Union in the early 60s made the remarkable discovery that actually not all of the intersection forms I've talked about could arise from smooth manifolds. What Rochlin showed is that if you had any smooth compact spin four-manifold, its signature is divisible by 16. So if you were to look at how many E8s this involved, it has to involve an even number of E8s. It can't have an odd number of E8s. Atiyah and Singer gave a proof of this, which I will tell you about at some point. I was hoping to get there today. I don't think we're going to get there. There's a more geometric proof of this, which is based on the Dirac operator, but it also involves the index theorem. All right, so so if you were to have if the even intersection form J E8s plus K H's were the intersection form of a smooth four-manifold, then the number of E8s would have to be even. Otherwise, the intersection form would merely be divisible by 8, not by 16. Donaldson shocked the world in his thesis, and he, in particular, completely shocked Michael Friedman when, by showing that if you have a smooth, compact, simply connected four-manifold, and if it has positive definite intersection form, then its intersection matrix is in fact the same as the connected sum of many copies of CP2, unless it's the four sphere, in which case it has kind of empty intersection matrix. Right? So if it has strictly positive definite intersection form, then its intersection form is odd, and it in fact is the same as that of a connected sum of CP2s, all with the same orientation. Personal story. This piece of news was, Donaldson's thesis was communicated by Atiyah to Friedman at the IHES, and I happened to be sitting at the next table at lunch while Atiyah told Friedman about this. And Friedman loudly said, "That's ridiculous, that can't possibly be true." And he set out to show that that Donaldson's claimed result was just absurd. By the next day, he had proved that, well, assuming that Donaldson is correct, it would follow that R4 had more than one smooth structure. And so we're not going to really talk about exotic R4s in this class. It's not something you need to understand. But Donaldson's thesis and theorems that Friedman had proved together, if they were both proved, Friedman discovered that it had to mean the thing that he had the reason he thought it was impossible was tacitly assuming there was only one smooth structure on R4 because Rn only has one smooth structure in other dimensions. All right, so this is actually the beginning of wild and wonderful things. Now, one of the basic constructions that's used in smooth topology is that of cobordism. If you have two n-dimensional, and I'll take them to be oriented manifolds, let's say Xn and Yn are two compact oriented n-manifolds, then you say that they are cobordant if there is an oriented manifold with boundary W in the next dimension up, whose boundary consists of a copy of Y and a copy of X with the opposite orientation. Y, the opposite orientation. So the basic example would be that anything should be cobordant to itself because you could cross it with the interval and you would get an oriented manifold that goes between a copy of the manifold and itself. But how do you orient boundaries normally? If there's an interior boundary, you orient the boundary components by saying you take the outpointing direction and you contract with the volume formula. So if in order to make this consistent with saying that any manifold is coordinate to itself, one component of the boundary is given the reverse orientation. So if you say that x is coordinate to y, it's saying that x bar, disjoint union y, form the oriented boundary of a compact oriented manifold boundary, the next dimension up. Now, so topologically, a cobordism could be very complicated, but there's an important subclass called an H cobordism. So you say that a cobordism is an H cobordism if the inclusion of x into W and also the inclusion of y into W are homotopy equivalences. In particular, that means that x would have to be homotopy equivalent to y. So Smale's big breakthrough in higher dimensions was eventually restated. There's a really beautiful book by Milner that describes the theory of H cobordisms. The H cobordism theorem of Smale is that suppose that you have two n-dimensional manifolds which are H coordinate in this sense. Suppose that one of them is simply connected, and by the definitions that says everything inside is simply connected. All right, so suppose that everything's simply connected, and also suppose that the dimension of this boundary is bigger than 4. Then it follows that that actually x is diffeomorphic to y. And the trick is that you can find a Morse function on W, which has x as one level set, y as a later level set, and then you have to make changes in the Morse function to eventually cancel out critical points and show that there's a Morse function that doesn't have any critical points, and then flowing along its gradient gives you a diffeomorphism between W and x times an interval. So there's this very delicate business of canceling critical points, canceling handles. On the other hand, there's a very interesting theorem in dimension 4 proved by CTC Wall, Terry Wall. And his theorem is that if you have two four-manifolds that are homotopy equivalent, and if they're simply connected, then in fact they're H coordinate. You can get this picture of some 5-manifold that negotiates between the two of them. Simply connected 5-manifold, linking these two simply connected homotopy equivalent 4-manifolds, and this manifold is homotopy equivalent to either boundary component. Now, Wall had a very interesting ulterior motive for proving this theorem. He deduced an amazing theorem about classification of smooth manifolds up to taking connected sums, up to stabilization by taking connected sums with S2 times S2s. We won't worry about that today. Wall found out that in dimension 4, homotopy equivalence of simply connected 4 manifolds implies that they're actually H coordinate. But, of course, that doesn't seem very useful. Smale had shown that his theorem only works starting in dimension 5. But what Friedman was able to do was he could carry out the proof that such cobordisms were trivial by working in the topological category. And so he replaced ordinary addition of handles with what are called Casson handles. So he was able to actually eventually show that, yes, you can carry out topologically, but not smoothly, the same cancellation procedure. And so Friedman was actually able to prove that if you have this picture, a simply connected 5-manifold, which is an H cobordism between two simply connected 4-manifolds, then it's in fact homeomorphic to a product, and therefore those two boundary components are actually homeomorphic to each other. All right, so the weird thing is that this all happens, you start off with smooth manifolds, everything in the middle is smooth, but the conclusion is topological. Now, when you put all of these pieces together, you get that theorem that I claimed before. Friedman and Donaldson's work together shows that if you have two smooth, compact, simply connected four manifolds, they're orientedly homeomorphic if and only if, and you can really just break it down to the following statements. They have the same Euler characteristic, they have the same signature, they're both spin or they're both non-spin. And if you like, I mean, usually there's an equivalent way of saying this. It's that they have the same B plus and they have the same B minus. But if you look at the formulas for the Euler characteristic and the signature in terms of B plus and B minus, these are equivalent statements. So, as I warned you before, the main hazard here is that this is only a classification up to homeomorphism, even though the manifolds you're talking about are smooth. It's not saying they're diffeomorphic, it's saying that they're homeomorphic. And so, in fact, there is no known diffeomorphism classification of four manifolds, even in the simply connected case. And in fact, what turns out you can show by using techniques I will tell you about, typically for one homeotype, there are actually infinitely many different inequivalent smooth structures. All right, so we saw as a corollary, for example, that if you had any non-spin compact, simply connected four manifold, then it would have to actually be homeomorphic to a connected sum of CP2s and CP2 bars. What about the spin case? Here we had, in this non-spin case, we had a beautiful list of what the possibilities were. Can we do that in the spin case? Well, we need some new building block, and the essential building block we need is the K3 manifold. So K3 K3 was named by André Vig in honor of Kummer, Kodaira, Kaler, and Kodaira, and the beautiful mountain K2 in Kashmir. Which sounds completely crazy, off topic. K2, what was it famous for? This was 1958 when Vay's report came out. The point was that K2 is the hardest mountain in the world to climb. It had only been climbed once by that time in 1954, and it was not climbed again until the 1970s. Many people tried, they usually died. It's a very, very dangerous mountain. Okay, so the subtle warning is that he expected K3 to be even more dangerous. All right, so, but the basic K3 are Kummer, Kaler, and Kodaira, and they all played a role. So this was initially defined not as a four manifold, but rather as a complex surface, a complex two manifold. The definition that comes out of the work of Kodaira is that it is a simply connected complex surface with C1 equal to 0. It turns out, what turns out is that there's only one deformation type. Any two K3s are actually there's a one parameter family of integrable complex structures, which allows you to move from one to the other. So that in particular means that any two complex surfaces with these very mild properties, the first Chern class in integer cohomology is 0, and it's simply connected. And actually, if it's simply connected, because it's simply connected, you could even just say C1 vanishes with real coefficients. Well, there's only one diffeomorphism type, and therefore, in this course, I'll often refer to the K3 manifold, and you could say as a smooth manifold, it's represented by any K3 surface. So this is a spin manifold with Euler characteristic 24 and signature minus 16. So B plus is 3, B minus is 19, and the point is its intersection form would be 2 copies of E8 plus 3 copies of the hyperbolic form. Notice, like Rockland was saying, that if you had a smooth, compact spin manifold, that it would have to have signature divisible by 16 if it is spin, and this is a spin manifold. All right, so what does this have to do with Kummer? I mean, Kummer was a guy in the 19th century, and this is something which is very much a late 20th century story. The sophisticated theory of K3 is in the late 20th century. So Kummer's construction is that you begin with a 4 torus modulo, there's a standard Z2 action you could impose. This can be described in various ways, but I'd like to describe it. There's a generalization of this which makes me want to describe it the following way. Think of T4 as the product of two tori. And on each 2 torus, there's a Z2 action which just flips the torus over. It's like you skew it on an axis and flip it 180 degrees. So, we flip our torus 180 degrees. All right, so that defines a Z2 action on T4. Do it simultaneously on both factors. Now, when you take the quotient of T4 mod Z2, it is not smooth because it has, so here there are 4 fixed points on each factor, so there are a total of 4 times 4 is 16 fixed points. Locally, at one of these fixed points, it looks like R4 modulo multiplication by minus 1. If you take the quotient of R4 minus, multiplying by minus 1, the origin is fixed, and a small sphere around the origin, which in R4 is an S3, becomes, the quotient is RP3. That's not simply connected. So what you would find is if you were to take a small neighborhood of one of those singular points, throw out the singular point, then what's left over is not simply connected. So this can't be a manifold. It's an orbifold. Orbifolds are things that are modeled on Euclidean space modulo a finite group, and these are the class of orbifolds with only isolated singularities. So this quotient is an orbifold, compact 4-dimensional orbifold with 16 isolated singularities. On the other hand, if you were to think about the neighborhood of one of those singular points, it is the boundary would be an RP3. An acute fact is that if you take the unit tangent bundle of S2, then in fact you can identify that with RP3, because a point in the unit tangent bundle if you have a tangent vector, a unit tangent vector on S2. You take the unit tangent bundle of S2, that looks like RP3. And the way you see that is that if you take a unit vector on S2, you think of the point as being a unit vector itself in R3, and then you can take the cross product. You've just generated an element of SO3. So the unit tangent bundle of S2 looks like SO3, and that in turn is diffeomorphic to RP3. So you can get rid of these singular points by cut out a neighborhood and replace it instead by a neighborhood of the zero section and for orientation reasons, I want to call this the cotangent bundle rather than the tangent bundle of S2. So what that construction gives you is a so-called the Kummer model of K3. Now this actually, I described before, K3 is a certain kind of complex surface. And what Kummer actually discovered was that there's a certain class of complex 4 tori modulo Z2, which arise as singular quartics in CP3. Here's what such an example looks like. What you do, the model for the four torus is that you take the Picard torus of a curve of genus 2, and then you think of, even better, take the component consisting of divisors of degree 2, and then there's an action of Z2 on it, which is induced by the Weierstrass involution. So what Kummer was able to show was that you could embed such quotients of a Picard torus of the curve of genus 2 as a singular surface in CP3. It's a singular quartic. And what you could do then is get rid of the singularity just by changing the equation slightly. So when I say it's, so a generic quartic in CP3 is an example of a K3 surface. I mean, the easiest, when I say, what do I mean by a generic quartic, it would be, for example, if you take the so-called Fermat quartic, take the sum of the fourth powers of the homogeneous coordinates and ask that their sum is 0, then that is a smooth quartic. And we'll exercise that this doesn't have any singular points. If you deform among all homogeneous quartics, the generic, the ones that have singularities are special there. So the complement has a complex codimension 1, and actually, therefore, its real codimension 2 is connected. So any two quartics actually are any quartic, non-singular quartic can be deformed into any other two non-singular quartics. Here is the kind of equation you need to get that picture. But the point is that, so it can be a very complicated looking quartic, but as the cartoon version is just think of the Fermat quartic. And that is, for K3, that's a perfectly good model. All right, so we were trying to narrow it down. We wanted to list, so here we found we could actually list homeotypes for the simply connected non-spin Four-Manifolds. There is a conjecture of what the possibilities are topologically for spin things. So up to change of orientation, the only possibilities would be, well, S4, of course, which has trivial intersection form, or you can take a connected sum of J copies of a K3 surface and K copies of S2 times S2. Now, so I say conjecture here, this is called the 11/8 conjecture because in the context of what's known from the work of Friedman and Donaldson, this is equivalent to saying that these conditions imply that the second Betty number is bigger than 11, or equal to 11/8 the signature. So if you look at all the intersection forms of these, they sweep out all possibilities that satisfy this inequality. There are in a positive direction, there is a beautiful result of Mikio Furuta, which says that with these hypotheses, the second Betty number must be bigger than 10/8 or 5/4 of absolute tau plus 2, as long as tau is not 0. So I mean, this is encouraging. That says that this has the right kind of field, but Furuta has spent much of the last 2 decades trying to improve his result to get to this inequality. And he actually, kind of wrote a long paper explaining it. His techniques can't get you there. We have no idea whether 11/8 is true or not, but you're certainly not going to see any examples in these lectures which would be a violation of this. You write down some Four-Manifolds by obvious operations, and you always get in this range. All right, so it's time for an intermission. Thank you for your patience, and let's take a break. So in this subject, one has to talk about a lot of simple fundamentals before actually getting to prove anything new. So I think that probably all of you have heard, or so many of you have already heard some of the things I've talked about today and we'll be talking about for the rest of this particular meeting. But I hope that, if so, if you've heard these things before, I hope that you will nonetheless get a different take on them and find that you've actually learned something new. Well, last time I introduced you to the fact that one of the fundamental peculiarities on an oriented four-manifold equipped with a Riemannian metric is that the two forms naturally split. The bundle of two forms splits into two rank 3 bundles. Namely, these are the eigenspaces of the Hodge star operator, and the eigenvalues that occur are plus and minus 1. So the forms that are sent to themselves by the Hodge star are called self-dual two forms, and the ones that are sent to minus themselves by the Hodge star are called anti-self-dual two forms. Now, it's not very hard to show that if you just think of the bundle of lambda plus over m, the definition involves the choice of a metric, but it's not very hard to show that if you choose two different metrics, the bundles as abstract bundles are isomorphic. So what are the characteristic classes of this rank 3 oriented vector bundle lambda plus over our four-manifold? So if you were trying to understand what it is topologically, you would focus on what are its characteristic classes. So if you have any smooth, compact, oriented four-manifold, one of the basic invariants you can attach to a bundle would be its first Pontryagin class. So what you can do is you can take its first Pontryagin class and pair that with the fundamental class, or if you like, integrate the first Pontryagin class of the bundle over the fundamental cycle. And the answer is that it's 2 chi plus 3 tau, twice the order characteristic plus 3 times the signature. And so this is often described as the first Pontryagin number of the bundle, because this is an element of, the first Pontryagin class is an element of H upper 4, that's just a copy of Z, and the isomorphism is given by integration or pairing with the fundamental cycle. So the first Pontryagin number of lambda plus turns out to be 2 chi plus 3 tau, and there are various interesting pure thought proofs of this nice fact, but I'm not going to burden you with any of these proofs right now. They take a while. But this is something worth thinking about on your own time. If you've forgotten what the first Pontryagin class of bundle is, this is an invariant of a real bundle, but it's related to Chern classes of the complex bundle you get by complexifying the real bundle. So this is something of real rank 3, and if you tensor it with, so this is something, the fiber looks like R3, you tensor it with C, you get something that has fiber C3, and then you could look at its second Chern class. So in general, the Pontryagin classes of a real bundle are the same as you tensor the bundle with C, take its even Chern classes, and then you alternate signs. So up to a sign, the Pontryagin classes are the same as even Chern classes. Where have we seen this expression before? 2 chi plus 3 tau. Remember the Hitchin-Thorpe inequality was saying that if you had an Einstein metric, this number, 2 chi plus 3 tau, would be non-negative. And actually, there is a direct way of seeing that. We're going to revisit the Hitchin-Thorpe inequality in a moment to see how this Pontryagin number comes into play. I won't constantly need other facts about lambda plus, but I already mentioned that, for example, the second Stiefel-Whitney class of lambda plus is the same as the second Stiefel-Whitney class of the four-manifold. This is an oriented bundle, so we're on an oriented four-manifold, so the W1 of both sides would be the same. The W2 would be non-trivial typically, and they're actually the same class. On the other hand, there's an interesting universal fact about this bundle lambda plus, which is a little bit subtle to show, which is that its Euler class is 0. So the Euler class of lambda plus would be, take a generic section. This is a rank 3 bundle on a four-manifold. That's a curve, right? So you take the vanishing set of a generic section of lambda plus. That's some curve. And this statement is that curve is always trivial in homology. A priori, for an odd rank bundle, it would turn out this was automatically something that's in two torsion. So there are many manifolds where there would be no place for it to live. But it's a little bit surprising that it always vanishes, and this is actually directly related to the fact that every four-manifold is in a C structure. Anyway, we said something about 2 chi plus 3 tau. And but we also related that to a Pontryagin number. So the basic lemma about, just kind of following through the definition, if you have a real vector bundle with an inner product on it, and that inner product is preserved by some connection. These are very weak conditions. So you choose an inner product, choose a connection that's compatible with it on the vector bundle. And then you're trying to understand what is this first Pontryagin number. So the first Pontryagin number, if you go back to the Chern, the Chern class definition, it would involve taking the curvature wedge itself and taking the trace. But because you can split two forms into self-dual and anti-self-dual parts, there's a beautiful way of expressing this by saying you take the self-dual part of the curvature, take it squared, its norm squared minus the anti-self-dual part, and now you integrate that on the manifold with a factor of 1 over 8 pi squared. That's this first Pontryagin number of the vector bundle. So here we're splitting the curvature, which is a bundle value two-form, into a self-dual two-form with values in a bundle, and an anti-self-dual two-form with values in a bundle. And in particular, what you would see is that if you have a self-dual instanton, so I mentioned Donaldson's beautiful invariants come out of the study of self-dual instantons. These are solutions of the Yang-Mills equation. So you can look at connections that have the special property that the anti-self-dual part vanishes. In other words, the curvature is the same as F plus. The curvature of the bundle is in fact a self-dual bundle value two-form. Then this instanton number must be non-negative. All right, so then P1, just by looking at the definition, F minus is 0, then this is non-negative, and it would be, you would get, it's equal to 0 if and only if nabla is flat, if it has 0 curvature. Now, we previously talked about, we introduced the pieces of the curvature tensor here by thinking of it as a linear map from two forms to two forms, and we saw that it was built out of the trace-free Ricci curvature, the self-dual and anti-self-dual Bow curvatures, and scalar curvature. It would turn out that just the first column here occurs as the curvature of lambda plus. And so if you take the Riemannian connection on lambda plus, it will turn out that F plus squared is scalar curvature squared over 12 plus 4W plus squared, and this is just going back to the fact that you're taking the norm of this piece with respect to an appropriate inner product. And then with respect to the appropriate inner product, it'll turn out that F minus has norm equal to the trace-free Ricci curvature squared, where its length is being, you're thinking of this as just its inner product of itself as a quadratic form on the tangent space. By the way, I should say that the conventions I use for W plus, instead you're thinking of W plus as W plus is really thought of as being a two-form with values in two forms, and the norm on two forms differs by a factor of 4 from taking the tensor norm. When you look in the literature, you may find funny factors of 4 in these Gauss-Bonnet formulas, and there are two different ways of thinking about the Bow curvature or the full curvature tensor. So check conventions, don't copy a formula from one paper, copy a formula from another paper, put them together, you find out you just proved that 1 is equal to 0, right? So, dangerous thing. You have to check your conventions, make sure you do. But if we, so the cute fact here, when is this connection a self-dual instanton? It's exactly when the metric is Einstein. So this curvature will be self-dual. In other words, lambda plus with its Riemannian connection will be a self-dual instanton if and only if the trace-free Ricci curvature vanishes, and that's the same as saying the metric is Einstein. If you were to look at the Riemannian connection on lambda minus with respect to the given orientation, it would turn out that Einstein was equivalent to that instead being an anti-self-dual instanton. Anyway, if you put these things together, you would just find from these kind of the definition of the first Pontryagin, with this, our formula for the first Pontryagin class. Here's a concrete way of writing the first Pontryagin class for lambda plus, and now you can simplify it, and it becomes the formula I wrote down before for 2 times the signature plus 3 times the signature plus twice the order characteristic. And you could, in the same way, get a formula for 2 chi minus 3 tau, because up to sign, that's related to the Pontryagin number for lambda minus. It's minus the Pontryagin number for lambda minus. Once you have these 2 formulas, this is just from the theory of Pontryagin classes, well, this implies a formula. You add and subtract these, you get formulas for the Euler characteristic and the signature. I mentioned them, I pulled them out of the hat before. I said there was a Gauss-Bonnet formula in 4 dimensions. If you prove this, you already have also proved the Gauss-Bonnet formula in 4 dimensions, and the signature formula. The tricky thing, I said before, by pure thought, not quick pure thought, you can show that the first Pontryagin number of lambda plus really is 2 chi plus 3 tau. All right, so we saw the Hitch-Thorpe inequality, as we proved it so far, is that if you have an Einstein metric on your manifold, then the 2 chi plus 3 tau must be non-negative, and it can only equal 0 if the induced connection on lambda plus is flat. And of course, the point is here, this is related to saying that this Pontryagin number is non-negative. This would be, physicists would call this the instanton number of the instanton. But on the other hand, what does it mean to say you have a Riemannian metric where the induced connection on lambda plus is flat? When does that happen? Well, to understand that, we need to discuss the notion of holonomian Riemannian geometry. So, one of the most important, simple ideas in Riemannian geometry is that of the holonomian group of a manifold. If you take a connected Riemannian manifold and choose some base point, which occasionally I'll call P, then associated with any loop, you can take any piecewise smooth loop based at P, and then there is a notion of parallel transport along piecewise smooth loops, and that gets you, starting with any initial vector at the base point, you get by parallel transport around that loop, you get a new vector, which is called its image under the holonomic transformation of the loop. So for every piecewise smooth loop at the with the given base point, you get a linear map from the tangent space at the base point to itself. That is in fact, because if you're using the Riemannian connection, then parallel transport preserves inner products. It preserves length of vectors. And so this, if we now identify the tangent space at the base point with Rn by choosing some orthonormal basis, what we get for each of such holonomic transformation is an element of On, but then if we take all holonomic transformations associated with all loops, you get, well, initially it's a subset of On, but then you can show it's actually a subgroup of On. If you follow one loop by another, these holonomic transformations compose. If you follow a loop backwards, it gives you the inverse holonomic transformation and so forth. So in fact, this defines a subgroup of On. It's a a remarkable fact that if your manifold is actually simply connected, the group that you get is actually a compact connected Lie subgroup of ON, and one of the great problems that came up in the 50s was to try to classify holonomic groups. That was the first huge leap in that direction was made by Marcel Berger. So he gave a list of candidates, which narrowed it down. Some turned out to, you could eliminate some candidates, and others turned out to really occur. So the study of Riemannian holonomy is a very central topic now in Riemannian geometry. Before Berger, it was actually his advisor, Schnellitz, pointed out that the notion of a Kähler metric is in fact equivalent to a statement about holonomy. Kähler wrote down this kind of horrible, just said, let's consider a metric that is gotten by taking the mixed partial second derivatives of some function on Cn and try to use that as and he discovered something amazing, namely the formula for the Ricci tensor had the same shape as that form of the metric. But it was sort of like, why would you ever consider such a metric? How to realize, well, there are lots of them because you have any submanifold, complex submanifolds of projective space, complex algebraic varieties naturally carry these Kähler metrics. But the notion from the point of view of holonomy is that a Riemannian metric is Kähler if and only if its holonomy group is a subgroup of UM, provided you've chosen a reasonable basis for your. So, I mean, really, when you say the holonomy group is a group of linear transformations of the tangent space of the base point, and this is the statement that if you choose the right identification of the tangent space of the base point with CM, you're in even dimensions, so R2M can be thought of as CM. If you make the right identification, the holonomy group becomes a subgroup of UM. So for a four-manifold, we'd be saying the holonomy is contained in U2. That's the same as saying that there is an almost complex structure, J. So this is equivalent to several conditions. The first is that there is a complex structure, J. An almost complex structure is a tensor field which defines an endomorphism of the tangent bundle with square minus 1. So this is something that could be used to thought of as a multiplication by I on each tangent space, makes each real tangent space into a complex vector space. There's an almost complex structure with the property that it's invariant under parallel transport, or equivalently, that it has covariant derivative 0. And, moreover, this J is chosen in such a way that the metric, if you pull back the metric with respect to J, it's unchanged. So G is J invariant. So the way you would produce this is if your holonomy is contained in UM, that's to say you have a multiplication by I on the tangent space, and you think of it as CM, you get a value of J at the base point. Then you can parallel transport it around, take it to any other point by some arbitrary path, and if it would turn out that's independent of path, because if it weren't, then you would produce a loop where the holonomy was not in the unitary. So this is an important dictionary. Now, but what does that imply? Here, if we just do it in dimension 4 for simplicity, then the first thing is we'll make our four-manifold into a complex manifold, a complex two-manifold. So the reason is that this condition that nabla J is equal to 0 actually implies that so nabla is a torsion-free connection, and there's something called the Nienhaus tensor, which you can take the covariant derivative of J with respect to any torsion-free connection, then you read off its J anti-invariant part, blah, blah. So there's a piece of it, which is the Nienhaus tensor, which turns out to be exactly the obstruction in the Neulander-Nierenberg theorem for an almost complex structure to be formally integrable. So already using the Neulander-Nierenberg theorem, so more generally, if there's a torsion-free connection with the property that nabla j is 0, then in fact you have local complex coordinates. An acute fact is the converse is also true. If you have complex coordinates and a Hermitian metric with respect to them, just given, if you have a complex structure, you can always find a torsion-free connection where such that J is actually invariant under parallel transport or parallel. All right, so the first thing is that this condition tells you you can make your manifold into a complex manifold, and you can also construct a closed J invariant 2 form. So the 2 form I'm talking about has the property that its pullback with respect to J is itself, and it's also closed, and since D of it is 0. By the way, if you already know your complex geometry, what I just said, this J invariance is exactly the statement that the omega is a real 1-1 form. Okay, so and then the other thing about this 2 form, it's not just any 2 form. You can actually reconstruct G from this so-called Kähler form by putting J in the second slot. So if you want to take the inner product of 2 vectors, apply omega to these 2 vectors, where the second one has to be rotated by J before you take the inner product. And in fact, the algorithm goes the other way. To get omega from G, you put J in the first slot. Now, actually, just to reassure you, so I emphasize the 4-dimensional case, but what I just said has nothing to do with 4 dimensions. If you're in any even dimension, and you're saying, when does a metric have holonomy in Riemannian holonomy in UM, then that's exactly equivalent to for example, this last property. If you look at a book like Griffiths and Harris, they'll never mention Riemannian holonomy. They'll never mention taking a covariant derivative of J or anything. And the point of view that was developed by Hodge and is now used by most people doing transcendental algebraic geometry is you start with a complex manifold endowed with a Kähler metric. And a Kähler metric means that you have a closed 2 form, which is positive in the sense that this expression gives a Kähler metric, and it's a closed form, which is of type 1-1. So you might not recognize the holonomy definition. It's often swept under the rug by even good books on offering an introduction to Kähler geometry. It's important to notice that since omega is a closed 2 form, it has a Durand class, and that is called the Kähler class of the metric. And it's a notion that will come back later. All right, so the key magical thing, which was really discovered by Kähler, but not put in these words. There's a different 2 form that you could cook up in an analogy to, so here this Kähler form is you take the metric and you put J in 1 slot, and that turns out to give you something that's skewed. If you take the Ricci curvature of a Kähler metric and you stick J in the first slot, then in fact that is a 2 form. This is skewed. It has to do with the fact that the Ricci curvature is actually invariant, and it's actually the Riemannian connection induces a connection on the canonical line bundle, which is the determinant line bundle of lambda 1, 0. So in complex dimension 2, that's taking lambda 2, 0, and complex dimension m would be taking lambda m 0. The connection on this induced by the Riemannian metric is actually just given in terms of the Ricci tensor, and moreover, this ends up giving you a beautiful formula for the Ricci tensor, just in terms of the volume form for the metric. All right, so we saw that the special property of Kähler metrics is that they have holonomy in UM. I didn't emphasize it enough before, but UM is by definition the set of orthogonal transformations on R2M, which are also complex linear, if you think of R2M as Cm. Right? That's the definition of UM. But what about Ricci flat Kähler metrics? If the Ricci tensor vanishes, we just saw that the curvature of the curvature of the canonical line bundle is actually determined by the Ricci tensor. So in fact, if you so SUM is the if the holonomy is in SUM, then your metric is Ricci flat and Kähler. Warning: this is not an if and only if yet. It's close to being an if and only if. So if you take the SUM is the set of elements of UM thought of as complex matrices where their complex determinant is 1. And to be Ricci flat is saying that the canonical line bundle is flat. That would mean that if you were to take if you were to take a loop coming back to the base point and ask what was the determinant of this, if your loop represents 0 in the fundamental group, if it's null homotopic, then it would turn out that the determinant of this holonomy transformation would automatically be 1. So in general, if the fundamental group is non-trivial, you can have monodromy depending upon which element your loop is in the fundamental group, represents what element of the fundamental group. But if you are on a simply connected manifold, this Ricci flat condition is exactly the same as having holonomy in SUM. And so this, in general, the holonomy SUM is a little bit stronger than being Ricci flat. Many people would say, introduce the word Calabi-Yau. For some people, Calabi-Yau would mean that you have a Ricci flat Kähler metric. Here, the definition I'm choosing, which is used by many people, is to instead say the holonomies in SUM is the condition to be Calabi-Yau. All right, so there's another class of metrics that come up in the theory of holonomy. These are not all of the holonomy groups, they are just the infinite series that I'm discussing right now. If you're in a dimension, a multiple of 4, then there's a notion of a hyper-Kähler metric, and that's saying that the holonomy is in SPK. And the convention I'm taking for the definition of SPK is that it is the set of orthogonal transformations in dimension 4K, which are right quaternion linear. All right, so there you can look at, so these are the orthogonal transformations that could be represented by a quaternionic matrix in dimension 4K. That's an important so-called classical Lie group. The name, the notation is based on the work of Hermann Weyl. So SPK is a subgroup of SUK, SU2K, and for that reason that hyper-Kähler manifolds are also Ricci flat, but they're actually Kähler in many different ways. So you could, so this is something where this group could be thought of as defined over the quaternions. You could single out the quaternion I and think that is the complex number I, and then express the other things as matrices. But you could also instead say, oh no, the quaternion J is what we think of as I, and then I and K are represented in terms of 2x2 matrices. So you, by doubling the size of the matrix, you can write, you can embed SPK and SUK in many different ways. There's sort of a natural two-sphere of different embeddings. This terminology was first introduced by Eugenio Calabi in, I believe, the early 1970s. But hyper-Kähler metrics, that's now the standard terminology. If we go down to dimension 4, it's often useful to talk about hyper-Kähler Four-Manifolds, but it's also important to keep in mind that in dimension 4, SP1 is the same as SU2. So the SP1 as a Lie group can think of it as the unit 3 sphere sitting in the quaternions, thought of as a multiplicative group. Take the non-zero quaternions as a multiplicative group. The unit 3 sphere is then a subgroup. On the other hand, you can also express that same group, instead of being a group of 1 by 1 quaternionic matrices, you can expand this in terms of complex matrices, and it will turn out to be all of SU2. And so, in particular, with the conventions I'm taking, in having holonomy SU2, holonomy SU2 is the same as having holonomy SP1, so Calabi, Yau, and hyperkähler are really the same thing in real dimension 4, complex dimension 2. On the other hand, if we have a four-manifold which is simply connected, being hyperkähler is exactly the same as being Ricci flat and Kähler. Warning, this is a standard pitfall. So if you allow non-simply connected manifolds, when you have a non-simply connected manifold, there can be some discrete extra piece of its holonomy that you don't see by just looking at that you don't get just from the loops that are homotopic to the identity. So there can be extra monodromy involved. So if I use the term locally hyperkähler, that means that the universal cover is hyperkähler, and in dimension 4, that's exactly saying that the manifold has reduced holonomy in SP1, where reduced holonomy means that rather than considering all loops, only consider those loops which are null contractible. Those are the ones that lift up the loops in the universal cover. The holonomy around such a loop exactly will correspond to holonomy transformation of the universal cover. But this locally hyperkähler will turn out to mean that, well, it's also something which is locally Ricci flat Kähler. Warning though, how do you know locally hyperkähler does not mean that you can find a complex structure on the manifold? There are examples which are not actually complex. Okay, so we said previously that the boundary case of the Hitchin-Thorpe inequality occurred when the induced connection on lambda plus is flat. But now, actually, it's not hard to see. This is exactly the same as saying that the manifold is locally hyperkähler. The reason is that rotation group O4 can be thought of as SP1 times SP1 mod Z2. To say that it's locally hyperkähler means that you don't see one of those SP1s. One of them is trivial. It doesn't occur from the holonomy. But that's exactly the one that would act. So the two different, I mean, you have really two different SO3s that come up at SP1 mod Z2, SP1 mod Z2, related to the fact that the group is SP1. In 4 dimensions, you could say that SO4, if you mod out by plus or minus the identity, this is actually isomorphic to the group SO3 times SO3, and this is the group that acts on lambda plus, and this is the group that acts on lambda minus. So, so the subgroup that acts trivially on lambda plus would be the one that projects to this SO3. But what subgroup is that? Well, you have sitting in here SU2 or SP1. This SP1, this is SP1 times SP1 mod Z2, but here, if you then further mod out by plus or minus the identity, what you're really doing is modding out by Z2 times Z2. And so the things that go to the identity here would turn out just to be SP1. They would be the things that corresponded to this second part of SP1. All right, so of course the difference between the two copies of SP1 is reflects the choice of an orientation. So the difference between the self-dual 2 forms and the anti-self-dual 2 forms depends on the choice of orientation. If you reverse the orientation, you get you would just interchange lambda plus and lambda minus. All right, so the amazing thing is you can completely classify the locally hyperkähler things in the following sense. This was done by Nigel Hitchen. The only possibilities are that the manifold up to finite cover is a flat 4 torus, or it is a Calabi-Yau K3. So we saw a cartoon version of K3 before. This is in Hitchen's paper of 1974. The analysis of this boundary case is really brilliant, and it has ramifications in the subject. So, for example, this depends on the Chaire-Gromov splitting theorem, which tells you that if you take a compact manifold of non-negative Ricci curvature, it has finite fundamental group, unless the manifold splits off a flat factor in the universal cover. But in dimension 4, a Ricci flat manifold that split off a flat factor would have to be, well, some Ricci flat 3 manifolds, say, times R Ricci flat 3 manifolds are flat. So the Chaire-Gromov splitting theorem guarantees that if it's not flat, its fundamental group is finite. So in this case, you could pass the universal, if the fundamental group is finite, you pass to its universal cover, and that will turn out to be a K3. The other possibility is that the universal cover could be the fundamental group is infinite, but then it turns out that the manifold is actually a 4 torus modulo a finite group. So there's very old work of Bieberbach before World War II on doing crystallography in higher dimensions, and his theorem, he didn't phrase it in this way, but it implies that actually in any dimension, if you have a compact flat manifold, then it is finitely covered by a flat torus. It's a very good theorem. Bieberbach was not a good man. He was a really a horrible Nazi that actually volunteered to go kill people, and not on the battlefield. On the other hand, why are these called Calabi-Yau manifolds? Well, it's because the existence of metrics of this kind depends upon a remarkable theorem. It's really what Yau got a Fields Medal for. Yau showed in the late 1970s that if you have a compact complex manifold of Kähler type, so if it admits any Kähler metrics, and if it has first Chern class 0, and here you don't even need first Chern class 0 in integer cohomology, it's good enough for it to be 0 in real cohomology. So that could be so C1 could be a torsion class. Then actually every Kähler class contains a unique Kähler metric that is Ricci flat. Okay, so the formalism that leads to this conclusion, to set this up as a PDE, was already done by Calabi in the 50s. Calabi thought he had proved that theorem, he had proved part of the theorem, but he was a geometer, not an analyst, and he didn't know how to finish off the difficult problem of proving existence of PDEs. Actually, Calabi told me the following funny story. He first sends his paper off to Andre Vey. Andre Vey, who is not a very kind person, right? He liked to put people down. So he wrote Calabi back saying, "You realize this isn't a proof, right?" And basically implicitly saying you're just some kind of incompetent moron. So Calabi kind of panics and he starts asking the best analysts he knows about, well, how do you go from what I've done to actually getting a proof of the theorem? And so he goes up to a blackboard in front of Louis Nirenberg, and Nirenberg listens to him for about 5 minutes, and he said, "Sit down. I'm going to tell you something, and I want you to write it down. You cannot prove existence to a nonlinear PDE without a priori estimates." And Calabi's reaction is, "What's an a priori estimate?" He was very proud of himself. A few years later, he proved an important a priori estimate for the real Mogent period equation that's related to this problem. He claimed to me that it was the best paper he ever wrote. I don't think that's true, but anyway, he was very proud of it. He learned something. That's the way we always feel when we learn something that we didn't know. Okay, so for the last part of the lecture, at the beginning of the lecture, we started by talking about how do you classify up to homeomorphism simply connected four-manifolds. But that was a discussion kind of in the vacuum. So I showed you some theorems that were about, well, you could construct them up to homeomorphism in certain ways. But how about real, interesting four-manifolds that come up in the wild? Well, here's a very interesting class. In CP3, you could consider a smooth hypersurface of degree n. So this is a so-called Fermat hypersurface of degree n. Take the sum of the four homogeneous coordinates, require that they're equal to 0, and it's a little exercise. That's actually a smooth, complex two-manifold, a real four-manifold sitting embedded in CP3. All right. So cartoon version. You just imagine it's something that's given by a homogeneous polynomial equation. Here I've drawn it in R3. You imagine that's sitting in RP3, but then you're supposed to complexify it, and it's in CP3. So it's a nice consequence of the Lefschetz hyperplane section theorem, which, if you know what that is, great. And if you don't, I'm just telling you what you could go to look up to figure out how you would prove such a statement. These are all simply connected. Okay, so these are all simply connected for any degree n. If n is even, this is a spin manifold. It is non-spin if n is odd, and you can compute b plus and b minus using some simple complex invariants. So, for example, the b plus b minus, these grow cubically in n, and the signature is a nice product of three consecutive integers of the same parity divided by 3 with a limited sign. Now, so the main question we'd like to ask is, this course I'm discussing the question of which smooth compact four manifolds admit Einstein metrics. Well, in terms of examples of manifolds, one rich source is you could look at complex geometry, and it turns out that what we'll eventually learn is that there are some smooth, there's some machinery for smooth manifolds involving the Seiberg-Witten equations, which allow you to mimic certain aspects of Kähler geometry when treating non-Kähler metrics. So a special case of the above question would be, suppose you have a compact complex surface, when does it admit an Einstein metric, and don't demand that the Einstein metric is related to J. The reason that this is a useful context is sometimes you can find an Einstein metric that is actually even related to your J. But sometimes you could instead show that even if you had an Einstein metric that was not related to J in any way, there'd be an obstruction. And we'll see cases where these two approaches sort of mesh perfectly. So I now want to talk about, so if we were just looking at complex surfaces, before I was talking about how do you classify smooth compact four manifolds. If we use as an important source complex two manifolds, complex surfaces, it turns out that Kodaira discovered a wonderful classification scheme for all compact complex surfaces. This is based on earlier work of the Italian School of Algebraic Geometry, notably in Greek ways, but now Kodaira did it in a completely different way, because he didn't assume he was looking at an algebraic variety, but instead just a smooth, compact, complex manifold. And so Kodaira's classification of complex surfaces, first of all, focuses, the most important invariant that Kodaira introduced is the so-called Kodaira dimension. So given a compact complex surface, one can define its Kodaira dimension, and here it looks maybe intimidating. What you're going to do is you take the holomorphic sections of positive powers of the canonical line bundle, ask what's the dimension of those sections, take the logarithm, and divide by the logarithm of this power, and then take the lim sup as L goes to infinity. Well, I don't know how you feel about it, but the first time I saw that definition, I didn't understand anything. The point is that it turns out that that actually these both roughly have polynomial growth, and you're asking what's the degree of the polynomial. So, in fact, the Kodaira dimension of a complex surface is either an integer 0, 1, or 2, or the other possibility is that it's minus infinity. Right. So here if all of these spaces are 0, if there aren't any holomorphic sections of any of these line bundles, then well this log would be minus infinity formally, and then you would find that the Kodaira dimension is minus infinity. So why is this essentially an integer? Well, in fact, it turns out to coincide with the following more geometric thing. You can try to embed, there's a nice map. For each of these line bundles, there's a natural map from the manifold to projective space of some dimension, which is that you take ratios of sections. So, strictly speaking, this projective space is the projective space of the dual of that vector space. There's a nice map. It's not defined everywhere, because if you have a point that's in the base locus of the system where every section vanishes, then that would be a point of indeterminacy. But what you can now say is that among all such maps, what's the maximum complex dimension of the image? And here we have the following weird convention. If it's always empty, because actually there aren't any sections, we say the dimension of the empty set is minus infinity. Well, anything you say about the empty set is true, right? So dimension of the empty set is defined to be minus infinity. All right, so if you take the maximum dimension of the image, in particular, it's got to be, this definition looks like it has to be an integer 0, 1, or 2, or maybe it's minus infinity. And it takes some work to show that these are actually the same. You can, there are results that generalize this to higher dimensions, but it's easiest in complex dimension 2. All right, so let's just see some very simple examples of Kodaira dimension. Some of the easiest complex surfaces you could think about would be, why don't you just take the product of two Riemann surfaces? Think of those as complex curves. You take two complex curves, you take the Cartesian product, and that is a complex two-manifold. Right? So then you can find the Kodaira dimension. Just it depends on the genus of the first factor, the genus of the second factor. So these two genera will determine the Kodaira dimension. So if the first factor has genus 0 and the second factor has anything, so the first thing is a two-sphere, and now that it has any value, any genus you like, the Kodaira dimension of the product will be minus infinity. And that corresponds to the fact that you cannot have the canonical line bundle that will have the property that when you restrict it to one of those two-sphere factors, any section has to vanish, because it's positive in that direction. If both factors have genus 1, so if you take, we're talking about a 4 torus right now, take a two-dimensional torus times a two-dimensional torus, think of that as a complex two-manifold, then the canonical line bundle is trivial. All of its powers are trivial, And so you'll find that all of those sections of the canonical line bundle, powers of the canonical line bundle have exactly a one-dimensional space of sections, and so the Canard dimension is 0. If the first factor has genus 1, and the second factor has a genus greater than or equal to 2, so this would be saying that the first thing is, in this direction, you can think of this as having a flat metric, and this is having a metric of negative curvature, then the Canard dimension turns out to be 1. And so the high genus Riemann surface has Canard dimension 1 by the same kind of definition. The number of sections of its canonical line bundle grows linearly. Now you've just put on a torus factor all of the sections of the canonical line bundle where its powers are just pullbacks of something from the second factor. And then if you take a product of two surfaces, of two curves of genus greater than or equal to 2, so those are two hyperbolic surfaces, or two things that you think of as negatively curved, then the Canard dimension of the product is 2. Now, in order to talk about the Canard classification, one also has to talk about the notion of blowing up. So there is a key construction called blowing up that allows you to produce new complex surfaces from old ones. So if you take a compact complex surface, you choose a point in it, then you could say, well, let's just replace that point by a CP1. Well, it's not obvious before you think about it that actually gives you, in a natural way, another smooth complex surface. But in fact, the new CP1 you could put in, you take its normal bundle to be O minus 1. That's, in other words, the topological line bundle on CP1. It's the one where the non-zero elements of the bundle, think of CP1 as the set of complex directions in C2. For every direction, you get a line to the origin, and you can make those into a line bundle. In fact, here's the picture. There's a natural way of thinking about this O minus 1 line bundle sits in the trivial bundle with fiber C2, because each fiber is by definition a certain line subbundle, a certain line in C2. When you put them together, here's the picture. And you might notice there's a beautiful map that collapses the zero section of the O minus 1 line bundle to 0, and away from the origin is a bihomomorphism between the complement of the zero section and C2 minus the origin. Pardon me, of course, I drew that picture over R. That's the usual trick. So here there is that model. That model shows you that if you blow up the origin, you can replace the origin in C2 with a CP1 of normal where the Euler class of its normal bundle is minus 1, and get something smooth. You use that as that. You literally use that as the local model, and that allows you to blow up points on your surface. How does that change the topology? The beautiful thing is that up to diffeomorphism, what we've done to our original manifold is we've taken a connected sum with CP2 bar. So if you take the O minus 1 line bundle and you add a point at infinity, that is actually that is a good model for CP2 bar. If you were to take the O plus 1 line bundle, the line bundle with Chern class 1, and add a point at infinity, then that can be identified literally with CP2. The reason is that you choose a point in CP2, say that's infinity, choose some line which you think of as the zero section, and then, well, you think of there's a map from CP2 minus this point to that line, which is you just join infinity to any other point, see where it hits the line. All right, so if you were to take CP2, choose some point, which you think of as infinity, choose some line, you think of that as the zero section. And now, points, so if you throw away this point, think of that as an infinity. The rest fibers over the line by joining any point to this point at infinity and now see where it hits the line. That gives you a bundle structure for CP2 minus a point. And you can check, well, it's just a matter of the Chern class here, the normal bundle, this is O of 1. So, so if you do that with, well, O minus 1, you can think of that as the conjugate, fiber-wise conjugate, that reverses the orientation. And so, CP2 bar can be thought of as the one-point compactification of the O minus 1 line bundle. But in this model, what have you done? If this is the way you take some neighborhood of the origin and replace a neighborhood of this point with a neighborhood of the origin in C2 via this process, well, what's happening at infinity? You're cutting a ball out of CP2 bar and the boundary of that ball. All right, so the change in diffeotype here is that you've taken a connected sum with CP2 bar on your original manifold. Of course, so people, it's a typical abuse in the literature. You'll say, well, if you blow up k points, you're taking n connected sum k CP2 bar. That doesn't tell you what the complex structure is. Here, this process of you could take k different points and blow each of those up, and that would be taking a connected sum with more CP2 bars. Well, that actually comes equipped with a particular complex structure. If you're describing it this way, you're saying, well, it's diffeomorphic to that. Happens to also have some complex structure, and I'm being sloppy because I'm not telling you which complex structure we're talking about. All right, so a complex surface is called minimal if it is not the blow-up of another complex surface. So if X does not occur as a blow-up, then it's said to be minimal. That turns out to be the same condition as saying that your X does not contain a holomorphically embedded CP1 where its self-intersection is -1. Or that's equivalent to saying the Euler class of its normal bundle is -1. Any complex surface can be obtained from a minimal surface by blowing up a finite number of times. This is a triviality, but this is an example of a deep triviality, essential triviality. The point is, just to make, if something is not minimal, you can find a CP1 in it such that you could collapse it. Whenever you do that, you're decreasing the second Betty number by 1. With computation, you're decreasing the second Betty number by 1. But you can't do that infinitely many times. Okay. So this is one of the deep trivialities of the subject. And so when we do this, you can always get any complex surface from a minimal complex surface by blowing up a certain number of times. And then one says that this minimal surface is a minimal model for M. It turns out the minimal model of X is unique if the Kadar dimension is not -infinity. In the case where the Kadar dimension is -infinity, you can construct lots of examples of different minimal models for the same manifold. Also, blowing up does not change the Kadar dimension. So if you have a minimal model for the complex surface, it's always one whose Kadar dimension is the same as the surface that you started with. And the last thing is that this notion of Kadar dimension is invariant under complex deformations. So, for example, if we were to look at the smooth hypersurfaces that we looked at a minute ago, we took some homogeneous polynomial degree n, and for each such thing, you get a complex surface. For example, if it's of degree 1, well, that would be saying you're taking in CP3, you're taking homogeneous degree 1 thing. That's just a hyperplane in CP3. That would be a CP2. CP2 is minimal, and it has Kadar dimension -infinity. If you take instead take a quadratic, so if it's x squared plus y squared plus z squared plus w squared is equal to 0, it's a cute piece of classical algebraic geometry that what you actually have is CP1 times CP1, and the geometric observation was really made by Christopher Wren in the 1600s. He discovered that a hyperboloid of one sheet has straight lines on it. It's ruled by straight lines, and that's the basis of this observation. A quadric in CP3, a smooth quadric in CP3 is actually bihomomorphic to CP1 times CP1. All right, so again, this is a minimal thing. Well, here we've got a different situation if we go to cubic surfaces. It turns out that any cubic is actually bihomomorphic to CP2 blown up at 6 points. And there were people that were completely obsessed by this that spent part of their career thinking about the geometry of cubics. Very interesting. This is an example where this is, so here one of these hypersurfaces is not minimal. This is the blow up of CP2 at 6 points in general position. If you take a quartic, I also already mentioned that quartic were examples of K3s. Not every K3 is a quartic. In fact, not every K3 is even, they're all Kähler, but they're not all algebraic varieties. You have a family of you can find choices of complex structures on K3s that are deformations of, say, this one, where you could take that particular one with, there are small deformations of the complex structure where it is not something that can be embedded in projective space. And if that seems strange to you, here's something that's easier, and it's a nice exercise to think about. If you take the generic torus of complex dimension 2, C2 model lattice, for generic lattices, you can't embed that in projective space. So there are lattices where you can. For example, if you take a product of two surfaces that are two elliptic curves, then it is projective algebraic. But there are choices of complex structure on a complex 2 torus where it's not embedded in projective space. Okay, so if the degree is large, so this is the case where the Kadeira dimension coincides with the complex dimension. These are called manifolds of general type, where the complex dimension coincides with the Kadeira dimension. And they're called general type in the following way. So here is some typical list, right? We let the degree go from small to suddenly it could be like bigger than 5. Most of them are of this type, where the Kadeira dimension is the same as the dimension. If you take, you could take transverse intersections of a lot of hypersurfaces in some larger projective space, cut out by homogeneous polynomials. Though, if you construct manifolds as so-called complete intersections that way, most of them are of general type, as long as there's some simple condition on the sum of the degrees. If it's large enough, it becomes of general type. All right, so in fact, these manifolds of general type, they're pretty concrete things. We'll meet lots of them. Here, I mean, this seems mysterious, but well, here's a list of lots of things of general type. Write down some homogeneous polynomial, large degree in 4 variables. You'll get a surface of general type, and there are many others. All right, so the sort of question that we'll be looking at in the next lecture, we've seen that half of these manifolds, if n is even, these are spin manifolds. If n is not even, then if n is odd, these are not spin manifolds. Now, the expectation people had on the basis of higher dimensions would be that, oh, well, the ones that are spin, there might be an obstruction to having a metric of positive scalar curvature. But the expectation was when n is odd, you should always have positive scalar curvature metrics. None of these, if n is greater than or equal, so all these have Riemannian metrics of positive scalar curvature, even Kähler metrics of positive scalar curvature. These do not have any positive scalar curvature metrics. And so what we'll develop in the next lecture will be ways of actually not just showing there's no positive scalar curvature metric, but showing that actually the integral of the scalar curvature squared cannot be small for any Riemannian metric on these things of general type. So we will come to that next time. These lower bounds for the integral of scalar curvature squared turn out to give you ways of sharpening. So if you think about the way we proved the Hitchin-Thorpe inequality, it was just saying, well, the integral of scalar curvature squared, that can't be negative. Well, what if you have a lower bound for the integral of scalar curvature squared? What if you have some other, even better bound for the integral of scalar curvature squared plus some multiple of the wild curvature squared? It'll turn out that there, on these manifolds, there will be, the Seiberg-Witten invariance will give us ways of getting such lower bounds, and you get stronger obstructions. So next time, I will put these examples in the broader context. We'll first learn about the Dirac operator, then the Seiberg-Witten equations, and start deducing general facts about the Riemannian geometry of this kind of class of four-manifold, and we'll also see how to extend these, eventually these results. They certainly extend to a lot of things that don't admit complex structures. But this is a good start. I'll stop for today. Any questions? If you need to leave, by all means, feel free to leave, because after all, we had just way late today, so you may be raring to go. But if anyone has a question, or if you want to ask questions in private, I'm at your disposition. Yes?
I didn't quite understand why, when you blow up points in a complex surface, it amounts to do collected sum with the reversed orientation on CP2. Why the reversed orientation?
Okay, so the reason is that, so this argument would be that you could think of, if you take CP2, you can think of this as the total space of the O1 line bundle on CP1, union a point at infinity.
Okay, this I get.
All right. So what you would like to now do is say, so there is a complex orientation on this. CP1, O1, this is the total space. This is a holomorphic line, but it has an orientation. All right, so if we instead now look at where is there an eraser? Anything to? There's no eraser. All right, so if you notice that there is a map, which is an isomorphism between O plus 1 and O minus 1, where this is not holomorphic. This is actually, what you're doing is conjugation. This is the dual of O1. And it's a general fact when you have if you're just thinking of this as the bad notation here, standard bad notation. I'm really thinking about the underlying smooth complex line bundle. And this is the one where the Chern class is +1, this is the one where the Chern class is -1, okay? There is a map from here to there just by conjugation. Choose an inner product, choose a Hermitian inner product on the fibers, and then there is an isomorphism between the bundle. It's a conjugate linear isomorphism between the bundle and its dual. This is not, so fiber-wise, this is not complex linear. So, but here, if we're thinking about the bundle sitting over CP1, and you could just forget about the map and just say, well, this has a complex structure, it has an orientation. Right? This has a complex structure, it has an orientation. Here we've kept the base direction the same, we've done conjugation in the fibers. This therefore reverses orientation in the fibers, and therefore on the whole space, it's orientation reversing. So if you think of CP2 bar as you take the O1 line bundle and you add a point, a model for CP2 bar is take the total space of O minus 1 over CP1 and add a point at infinity. Now, the thing that to keep in mind is that, so away from this point, there is a complex structure on this. At the added point, there's no prescription given of how you would extend a complex structure, and in fact, you can show that it can't be extended, okay? This, here you have a complex manifold, you've added a point at infinity, it was a complex manifold, you compactified it merely as a four-manifold, okay? Is that all clear? All right, so you can think of, this is a model of CP2 bar. Now, what you're really doing here, so in particular, if you were to take CP2 bar minus a ball, then you could think of this as the unit disk bundle. Let's just say it's contained in the total space of O minus 1 fibered over CP1. This is terrible chalk. I'm so glad I'm not having to write on this blackboard. To get a different kind of chalk to write on. Is the white chalk any better? All right, so if you were to take CP2 minus a standard 4 ball, you could think of that as an open set in the O minus 1 line bundle over CP1. And what open set would you be looking at? Well, you would be taking some neighborhood of the zero section. You could think of that as you take the unit ball in C2, say, and you've blown up a point in it. Okay? So this is the total space of the blow up. Now, so in other words, if you were taking a connected sum, if you were taking a connected sum of your manifold with this, what you would do is you would take M minus a ball, and then you would take the union of that with CP2 bar minus a ball. But a model that I hope I've just convinced you that a correct model for CP2 minus a ball is you take a ball of some finite radius in C2, blow up the origin. Okay? Now you're going to glue those two things on the boundary. Well, concretely, you could just say, replace this ball with the blow up of a ball. So that's the connected sum. Okay. So these things are hard to digest at first. I mean, the funny thing about mathematics is sometimes that things that are elaborate and theoretical are very hard to get, are very easy to kind of understand immediately. It's language, right? You have a picture, you have to think about the picture for a while. You have to think about this picture. But the point is that when you take, so if you were to take, you could take C2 blown up the origin, that is actually the total space of this line bundle. And if you compactify it, you have a model for CP2 bar. Cut out a ball around infinity, you're just saying, well, let's not take all of C2, let's just take a ball and blow it up. And now you see, well, in this construction, you're really just replacing a given ball in the manifold with a ball that's been blown up at a point. You see that it's actually just taking a connected sum with CP2 bar. Yeah, so I'm glad that you asked this question, because one of these things, I have talked to people who they copy it down from someplace. They say, oh yeah, the blow up. They have no idea what's true. It's really, this is a nice pictorial exercise.
Is this related to the fact that O minus 1 is the canonical, the tautological bundle, line bundle?
It's related to the fact that this O minus 1, this tautological bundle, is in fact a subbundle of the rank 2 vector bundle, right? So, so you could say that this O minus 1 over CP1 naturally sits inside of, you take CP1 times C2, and you take that trivial bundle, well, then there is an inclusion like that. And so the way I was showing you to think about the blowdown is that, well, here, this bundle obviously has a map to C2. Just forget one factor. But now it's an interesting map when you take this inclusion and you compose with that projection. So that gives you a tautological map from the O minus 1 line bundle to C2.
Right.
And that's exactly blowing down. That's this blowing down map. Other questions? If you're shy, come ask questions in private, même en français. Je serais même ravi de répondre à des questions.